Hi, this is Professor Sartor. In this video, we're going to be approximating area under the curve. In mathematics, there are some formulas for area under the curve, but in this video, we're really trying to take it slow and lay some groundwork so that you understand the notation that's used in the formulas later on and what every part of the formula means. Now, although in this video we're going to start with approximating the area, we're actually interested in finding the exact area under the curve. With our geometry formulas, we're limited to figures like squares, rectangles, triangles, trapezoids. None of these have a curved side. And that's why we're going to be starting with approximating the area and hoping that this path we go down leads to finding the exact area under the curve. The example we're working with today says approximate the area under the curve f of x equals negative x squared from x equals 0 to x equals 2 with 5 rectangles of equal width. I went ahead and I drew the curve that we're dealing with. F of x equals negative x squared. X squared means we have a parabola. The negative, that parabola is facing down, and the plus 5 has shifted that figure up 5 units. So that's the parabola facing down, shifted up 5 units. We want to find the area under the curve from x equals 0 to x equals 2. So on my figure, I've got x equals 0 right here at the origin, x equals 2, and I'm going to draw vertical lines going up to the curve. And we want to find the area under the curve in between x equals 0 and x equals 2. So this is the area that we're interested in approximating. Now for this example, we are going to use 5 rectangles of equal width to approximate that area. The width of each rectangle, we're going to use the symbols delta x to represent that. So the width of each rectangle is delta x. So to get that width of each rectangle, we'll take the total width that we have and we're going to divide that by the 5 rectangles. So to find delta x, we're taking the total width and dividing that by the number of rectangles. For this example, you can easily see that this width, this total width, is 2 units, and we're having 5 rectangles, so for our example, delta x will be 2/5. Now, to speak more generally, we would normally label our lower bound of the interval with A and our upper bound of the interval as B, and then we can find the total width by doing B minus A. And we're going to divide by the number of rectangles, which we label as N. So now we have a formula where in general we're going to be able to find the width of each rectangle as long as we are making each rectangle have equal width. Now I'd like to take a minute to draw a more detailed picture of what our graph is going to look like and where the rectangles are going to lie. So I'm going to start with my x-axis, and remember that the beginning is at 0. We started x equals 0, and that is also our A. And we decided that our rectangles will be of width 2/5. So I'm going to start at that a equals 0 and move over 2/5. And that would mark out one of our rectangles. Going another 2/5 to 4/5, that's another rectangle. Then to 6/5, 8/5, and then 10/5. 10/5 is the same thing as 2, so that's the end of our interval. So you can see we've got our 1, 2, 3, 4, 5 rectangles. Let me draw the rest of that picture. We'd have our parabola up 5, coming down just about like this. Now, I want to draw the rectangles, and there are two different ways to draw the rectangles: inscribed and circumscribed. I'm going to start with inscribed. So, for each one of these values, I go up to the curve. And we're going to use one of the sides of our rectangles as the height of the rectangle. So what I'm saying is that I'm either going to use the left end as the height or the right end as the height. In this example, in this picture, I'm doing inscribed. And an inscribed rectangle is going to be inside the curve. So to keep my rectangle inside the curve, I'm going to use the right side, and the reason why I'm using the right side is because it is lower. That would keep the rectangle on the inside. For this next one, you can see that the right will be on the inside as well. So for all of these, I'm using the right side as the height of the rectangle. Now I'll show you the circumscribed, but give me a moment to draw the picture. So I've drawn the same starting picture, but this time I want to draw my rectangles circumscribed. And circumscribed is when your rectangle is actually a little bit larger than the curve. So looking at the two endpoints, to the left and to the right, the left endpoint is a little bit higher, so I'm going to use that as the height to create a circumscribed triangle. So either one of these can be used to approximate the area under the curve. However, they're each going to offer us something slightly different. The inscribed group of rectangles will give us the area under the curve, an approximation of the area under the curve, but we know because each rectangle is inside, it will be less than the actual area. However, the circumscribed group of rectangles, since each one of those rectangles are slightly larger than the actual curve, these will be more than the actual area. And we're going to find that area approximation by summing or adding the area of each individual rectangle. So if I were to find the area of rectangle 1 here, add it to area of rectangle 2, add it to area of rectangle 3, add it to area of rectangle 4, add it to area of rectangle 5, we're going to get that approximate area. So we're going to use something called summation notation, or sigma notation. This is the Greek letter sigma used to mean we're adding up. And we're going to add up the area of each rectangle. So now what we want to do is to come up with a formula for finding the area of each rectangle. When you find the area of a rectangle, we typically use the formula length times width. But I think it makes sense based on the way that the picture looks for us to use width times height. So let's take a look at a closer look at our picture to see if we can figure out how to write it, how to write the area of the rectangle. So I'm meaning for this to represent the width. Let me highlight that for you. And then we have our height of the rectangle being here. So based on the way that we constructed these rectangles, remember that the width was the same for every rectangle, and we labeled that width as being delta x. The height of each one of these rectangles is going to change every time. But if you look at the height of each one of these, you notice that these points that we're using for the height, all of them are on the curve. Let me go to the circumscribed. All of these heights are on the curve. So we're going to be able to use our function f of x equals negative x squared plus 5 as part of the way to get the height. And I also want you to notice that in the inscribed, we used the right endpoints, and in the circumscribed, we used the left endpoints. And we used those right and left endpoints to define the height of the rectangle. So the height part of our formula is going to be f, and we're going to plug in one of our endpoints. And it really depends on what your picture looks like, of whether you're going to use right endpoints or left endpoints. We're getting a little bit closer to having a formula for the area of each rectangle. But now we need to take a little bit closer look at this endpoint idea. I've already said we've got right endpoints and left endpoints. So let's take a look at how we might be able to write those with a formula in a little bit more detail. So let's take a look at our endpoints that we have. We had 0, 2/5, 4/5, 6/5, 8/5, and 10/5. You can see that those are all multiples of 2/5. So we can actually use a sequence to define those endpoints. Those right endpoints we can use the sequence 2/5 I, where I goes from 1 to 5. 5 for 5 rectangles. So let's just double check that. For I equals 1, 2/5 times 1 is 2/5. That gives me the first right endpoint. For I equals 2, that's 2/5 times 2, that's 4/5. For I equals 3, 2/5 times 3 is 6/5. Then we have I equals 4, that's 2/5 times 4, that's 8/5. And then finally, if I equals 5, we have 2/5 times 5, that's 10/5, which is 2. Then we're going to be able to get the left endpoints by shifting to the right. So we're going to make this I minus 1 from I equal 1 to 5. 2/5 times I minus 1 from I equal 1 to 5. So let's take a look at that and make sure it matches with the left endpoints that we have. So for I equals 1, that would give us 2/5 times 1 minus 1. That's 2/5 times 0, which is 0. That is our first left endpoint. And for I equals 2, that would give me 2/5 times 2 minus 1. That's 2/5 times 1, which is 2/5. That's our next endpoint. I equals 3. 2/5 times 3 minus 1. That's 2/5 times 2, and that's 4/5. I equals 4. 2/5 times 4 minus 1 is 2/5 times 3, and that's 6/5. And then finally, for I equals 5, that's 2/5 times 5 minus 1, 2/5 times 4, and that's 8/5. And that matches each one of the left endpoints that we had for our figure. So now making sure we go back to generalities instead of for our specific example, speaking in general about this, the right endpoints can be found with the sequence of delta x times I. Remember that 2/5 that we were using in this example? That 2/5 is, excuse me, I accidentally erased that 2/5. That 2/5 that we were doing in this example, or using in this example, is the delta x. The left endpoints can be found with the sequence delta x times I minus 1. So now if we go back to finding the area of each rectangle, we have a much more detailed formula. We had delta x times f at an endpoint. That's the y value at a particular endpoint. So it's going to be delta x times f of, now this part depends on whether you're looking for right endpoints or left endpoints. Let's assume we're doing right endpoints for this example, and we would put delta x I. So now let's take a moment to summarize everything into a formula for our circumscribed area and our inscribed area. So if you remember, what we were doing is we had 5 rectangles. So we're going to sum from I equals 1 to 5 for each of those 5 rectangles. And we need to find the area of each rectangle. And what we found is that we can find the area of each rectangle by doing the width times the height. And then we had formulas for the width. The width was the same for each rectangle. We called that delta x. And the height, those were the y values at the endpoints. And specifically for the circumscribed rectangles, those were the left endpoints. we got a formula for the left endpoints, and the formula for the left endpoints is delta x times I minus 1. So filling in the details for our particular example, the delta x was 2/5. We have f at 2/5 times I minus 1. And then the f of x for our example is negative x squared plus 5. So I can also fill that in. So everywhere I see an x, I'm changing it to 2/5 I minus 1. That'd be negative 2/5 I minus 1 squared plus 5. I can do the same thing for my inscribed area. We're going to sum those 5 rectangles from I equals 1 to 5. We are summing the width times the height. The width was delta x. The height was defined by the right endpoints for the inscribed area. We had a formula for the right endpoints, and that formula for the right endpoints was delta x times I. So delta x for our example was 2/5. So we have 2/5 times f of 2/5 I. And then let's substitute into our formula for f of x. And that would give me negative x, not x, negative 2/5 I squared plus 5. So that's going to give us our formula for the inscribed area. I'm going to show you how we simplify this, how we work this out by hand. So I'm going to start by simplifying this exponent. That would be 4/5 4/25 I squared plus 5. I'm going to use the distributive property with this 2/5. That would give me negative 8 over 125 I squared plus 10 over 5. 10 over 5 can be reduced down to 2. So I'm finding the sum of I equals 1 to 5 of negative 8 over 125 I squared plus 2. So one of the properties of the summation notation is that if you have an addition, if you have separate terms inside your summation, you can apply the summation to each term. So I'm going to do that. I'm going to apply I equals 1 to 5 of negative 8 over 125 I squared plus the sum of I equals 1 to 5 of 2. Another property of the summation is that you can pull out a constant multiple. So I'm going to pull out negative 8 over 125. I equals 1 to 5 of I squared. And when we get to this point, we have a few formulas that are going to help us to work out this final bit. So the summation formulas we're going to use are written down on the side here. The first one is sum of a constant. Sum I equals 1 to n of a constant is that constant times n. The next one is sum I equals 1 to n of I squared, and that's n times n plus 1 times 2n plus 1 over 6. So let me show you how they're used on this example. I'm carrying down that constant of -8 over 125, and I'm going to multiply by, since this is sum I equals 1 to 5 of I squared, I'm going to use this formula here. The n for ours is 5. So I'm going to put 5 here, here, and here. So this is 5 times 5 plus 1 times 2 times 5 plus 1 over 6. On the next part, we have sum I equals 1 to 5 of 2. 2 is a constant, so I'm going to use this formula to work that out. With n being 5, my constant times n, my constant times 5. So that's going to be 2 times 5. So I'm going to continue to simplify. I have -8 over 125 times 5 times 6 times 11 over 6 plus 10. 2 times 5 is 10. -8 over 125. Let's see. The 6's will cancel out, giving me 5 times 11 plus 10. -8 over 125 times 5 times 11 plus 10. These 5 will cancel out with a 5 here, making this 25. I have -8 over 25 times 11 plus 10. That's -88 over 25 plus 10. It's -88 over 25. I need a common denominator to combine these together. So 10 over 1 times 25 over 25. That gives me 250 over 25. And 162 over 25. If we put that in a calculator, that's approximately 6.48. So I wanted to bring us back to the picture that we drew near the beginning of this and remind you that the area of the inscribed rectangles, because those rectangles are inside the curve, are going to be smaller than the actual area. So that 6.48 approximation that we just got, we know is below the actual area. I'm going to leave for an example for you guys to work out the circumscribed area yourself, but if you do, you would get 8.08. So that gives us a boundary for knowing the actual area or the exact area under the curve. We know that it's somewhere in between 6.48 and 8.08. That leads us to next thinking about how we might get a better approximation. By only using 5 rectangles, we're leaving all this space that we're getting an error in our estimate. If we would increase the number of rectangles, we're going to get a better approximation. I'll also leave for you guys to try for yourself. If you do this with 25 rectangles instead of 5 rectangles, you're going to get your lower bound or your inscribed area as 1.1712, and for your circumscribed area, 7.4912. So you're getting a better approximation. You see that's a narrower window for that actual area, or the exact area to be in. So our strategy moving forward to transition from approximation to finding the exact area is to increase the number of rectangles, and that's dependent on the value of n.